Welcome back. Last lesson we looked at differentiation by first principles, where we were finding the derivative or the gradient of the tangent at a point of any function, and we had that big long limit equation to work out. This lesson we're looking at some shortcuts, but general rules you can use to find the differentiate any function that you have. So if we have a generic equation, let's call it f of x equals to ax to the power of n, then the derivative is equal to f dash x, which would be a times n times x to the power of n minus 1. And when you look at that, it can look quite confusing at first, but let's have a look at how we use that in practice. So all we're doing in simple is take the power of x, multiply it out the front, multiply the coefficient, and then we drop the power of x down by 1. So last lesson we looked at the example we looked at x squared plus 2x was our original function. So I'm going to use the notation y equals. So derivative, or dy dx, in this case we take the power, which is 2, multiply the front, 2x, and then the power of x drops down to 1. And what we can do is, if we've got a plus or minus in between, we just do the same thing for the next term. So treat every individual term as a separate function. So 2x, which is the same as 2x power of 1. Then we go the power of x, which is 1, times coefficient is 2. So that means we've got a 2 out the front. And then x, 1 minus 1 is 0. So our final equation is 2x plus 2, which is the same that we did in the first video, but it took us a good 8 minutes. So there's a nice little quick shortcut. Now, a couple other rules you might see if we have the differentiation of two separate things. So y equals, let's say, f of x plus or minus g of x. So we've got two separate terms. Then dy dx, we just differentiate each of those individually. And the plus and minus stays the same. So that's what we did in this example here. We had x squared and 2x, and we just differentiated them using that shortcut one at a time, and the plus stayed the same. Okay, that's a nice, quick and easy way of doing it. Let's have a look at 4 little examples. We've got f of x equals 6, or x to the power of 6, x to the power of 6, so therefore the derivative would equal, now if there's nothing written at the front, there's always a 1 there, so that'd be 6 times 1 is 6, and then that'd be x to the power of 5. And that's it. That's your answer. Let's do part B. F of x equals 4x to the 5. So we go 5 times 4 gives us 9. This is a differentiation. 9x to the power of 4. Power drops down by 1. Part C and D, we've got a little bit more complex equations to start with. So we've got y equals 4x cubed minus 3x plus 2, and we just treat them as each term individually. So dy dx, differentiate the 4x cubed first, so that'd become 12x squared. Then minus 3x, that's x to the power of 1, so then that'd become minus 3x to the power of 0, which is 1. And here, 2, that's the same as 2 times x to the power of 0. Well, 0 times 2 is going to be 0. Doesn't matter if it's x to the power of negative 1. It'd still work, but you've got 0 times that, so the whole thing drops off. So any constant term, gone. So that's our final answer, 12x squared minus 3. Part D. Looks a little bit more complex. We've got a term outside. Now we could multiply all that through, expand that bracket out first and differentiate, but we can treat that as a constant term because at the end we're going to have 1/3 times it anyway. So dy dx, we can just differentiate inside first. So we'd have 3x squared minus 3, and then multiply all that by 1/3 anyway. So we'd end up with x squared minus 1. If we want to check that, let's do the original question again, but let's multiply the third through first. So we get 1/3 x cubed minus x plus 2, and then divide x. 3 times a third is 1, so we get 1x squared, and then 1 times -1 minus 1 plus 2, which is constant, drops off, so with x squared minus 1. Either way, you should get the same answer. Okay, hopefully you find these a little bit more straightforward than the first part. Once you've seen this technique, chances are you'll never want to go back to first principles, so make sure you've tried that before you do this shortcut, because that's conceptually showing you where these ideas are coming from and how we know these answers are correct by using that differentiation by first principles. All the best for exercise 17B and C.